and where we left off was quotient rule. So I want everyone to take the derivative of sine x over cosine x. Right. So quotient rule, if I take the derivative of the top is going to be cosine times the bottom, which is cosine, minus derivative of the bottom, which is negative sine, times the top, which is sine x, all over the bottom squared. So I get cosine x squared. So you just plug it in, right? Of course, now we're going to clean it up a little bit. And when I clean this up, well, cosine times cosine is going to give me cosine squared x. The minus, this cancels, so I end up with plus sine squared x all over cosine squared x. All right. I do want to refresh your memory on the worst notation in the history of anything, and that is cosine x quantity squared. We don't write it that way, we write it this way, and to be honest, if I could delete that from every textbook ever, I would, because all it does is confuse people, but I can't delete it, so I've got to make sure you know how to use it. So I have to write it this way. So that cosine x quantity squared, that's this cosine squared x. But we're not quite done because I have this sine squared plus cosine squared. So what does that sound familiar like from last year? What does sine squared plus cosine squared equal? 1, right? That's our the one trig identity that you need to remember from last year. And so we end up with 1 over cosine squared x. And what does 1 over cosine equal? That's one of the other trig functions. What is it? Secant. And so this equals secant squared x, because it's squared. So if y equals sine x over cosine x, then y prime is going to equal secant squared x. All right. Well, while we're on the topic of just random trig functions, I'm interested in if y is equal to 1 over cosine x. I want the derivative of this. And you have to use quotient rule in this case. Now, like if it was just 1 over x, you could rewrite it as x to a power, but we can't rewrite this as x to a power because there's a cosine attached to it. At any time you have a fraction that you cannot rewrite as like an x to a power, then you've got to use quotient rule. So I want everyone to use quotient rule on this, and then sort of pause. We know that the derivative of sine x is equal to cosine x. Okay? That's what we know. We also know that the derivative of cosine x is negative sine x. That's what we knew, well, sort of, maybe we don't know it real well, but that's what I've talked about, right? I didn't prove it, I just sort of said, here's magic happens, and that's what we get. But we'd like to know some of the other trig functions, like, I'd like to know, well, what's the derivative of tangent, and what's the derivative of secant, and then what's the derivative of cotangent, and the derivative of cosecant. Yeah, but we just did, because what's sine over cosine? Tangent. And when we computed that, what did we find the derivative of tangent x to be? Secant squared x. Right. And while we're on the topic of randomly doing stuff, what's 1 over cosine? Secant. And we just computed the derivative of secant was equal to secant x tangent x. And so this is going to be secant x tangent x. Oh, well, of my 6 trig functions, I've gotten 4 of them. Now, to be honest, how you find the derivatives of the other 2, you kind of do the same thing. Like cotangent, you put that as cosine over sine, then use quotient rule and take the derivative. I'm not going to go through that, I'm just going to tell you the answer. Same thing for secant, you would write it as 1 over cosecant, you would write that as 1 over sine, do quotient rule, figure out your answer. Again, I'm not going to go through that, I'm just going to tell you what the answer is. So it turns out the derivative of cotangent is equal to negative cosecant squared. And the derivative of cosecant is equal to negative cosecant, and I went off the screen, didn't I? Negative cosecant x cotangent x. All right, so here's our little chart. I mean, usually they have this little, actually your book doesn't make the chart, but a lot of calculus books, they make a little chart of your derivatives of trig functions. And you need to know this. I mean, technically you don't, because I remember when I was in high school in calculus, I never memorized them. I knew I could derive it, so anytime I needed to know the derivative of tangent, I would do the little quotient rule real quick. Whenever I needed to do cosecant, again, I would do the little quotient rule and I would compute it. And then the problem is, it's not efficient doing it that way. There's very few things that I say, sorry, suck it up and memorize it. This is one of the things where I'm going to say, hey, suck it up, you've got to memorize it. And since I'm telling you to memorize it, I probably should give you some patterns I found out, right? So first pattern, very obvious pattern. All the cofunctions, the derivative is negative. So if you look at this, see, no cofunctions, everything's positive. Sine is positive, cosine, tangent's positive, secant's positive, secant's edge, right? Derivative of cosine is negative sine, derivative of cotangent, negative cosecant squared, derivative of cosecant, negative cosecant cotangent. Right? So obvious pattern. All cofunctions, derivative of all cofunctions are negative. Okay, fine. Next little pattern. You notice that secant and tangent kind of go together? And then cosecant and cotangent kind of go together? Like you never have a tangent with a cosecant, right? You have secant and tangent, and you have cosecant and tangent. Cotangent and cosecant, right?
Co's go together.
The cos go together here, right? And the non-cos. Except for the sine and cosine part, right? Okay. So of our patterns, let's see. What I've found is most people are fine with derivative of sine is cosine, derivative of cosine is negative sine. Most people remember that forever, that's fine. Right? I think most people easily remember that if it's a derivative of a cofunction, it's negative, so that part's fine. It's helpful to remember, all right, the secants and tangents go together and the cosecants and the cotangents go together. Right? Last pattern, and this is me being really silly. And this is incredibly silly and very childish, right? Right? I'm already doing the preface, this is incredibly silly and childish, right? In remembering these, you know, secant squared, that's like secant times secant, right? So when I look at this line, this whole line, I see two secants and one tangent. Did everybody see that? Two secants, one tangent. Two secants, one tangent. And then when I look at this line, I see two secants, one tangent. Two secants, one tangent. Everybody see that? All right? And same thing over here. Two cosecants, one cotangent. Right? Two cosecants, one cotangent. And if I look at this line, I see two cosecants, one cotangent. Two cosecants, one cotangent. I'm going to admit it. It's incredibly childish and silly, right? Very childish and silly. But you know what?
It works.
You'll remember it. And if it helps you remember it, I don't care how childish and silly a pattern I give you, right? All right, so here's what I need you to do. Now, I can force the 3 people in class to do this, all right? All right, here's what I need everybody to do. And you at home, you in the virtual world, I can't force you because all I'm seeing are dots with initials, right? That's what I teach you every day, dots with initials. But if you have any desire to learn this, please play along, right? And here's what we're doing. I want everyone to get a new sheet of paper. Flip over to a new sheet of paper, all right? All right? I do not want anybody looking at your notes. I want a new sheet of paper. Everybody's got, okay, I'm going to give you time to get a new sheet of paper. I'm not going to grade it, but I need you to have a new sheet of paper.
You're going to have us try and see if we remember it. Oh, no.
All right, create your chart.
Oh, boy.
Create the chart. We need to know what the derivative of sine x is. What's the derivative of cosine? What's the derivative of tangent? What's the derivative of secant? What's the derivative of cotangent x. Let's remove cosecant x. What do you do? Well, okay, derivative of sine is cosine x, derivative of cosine is negative sine x. You know what? Derivative of all cofunctions, those are negative. I'll just go ahead and put my minus sign. Right? I know that tangents and secants go together, and then I had that crazy math teacher tell me 2 secants, 1 tangent. Tangents and secants go together. I've got 1 secant here, so my second secant's over here. And then I've got a tangent, right? 2 secants, 1 tangent, 2 secants, 1 tangent. I need a secant here. I need a cosecant. And there's 2 of them, so I better square it. And then I better have 2 secants, 1 cotangent here, so I get cosecant x, cotangent x. Now, this is only for people who are interested in learning, remembering it, right? If you're not interested in remembering this, you can do whatever you want to, right? But if you have the slightest bit of interest in making sure you remember this, for the next few days, anytime you take derivatives of trig functions, make this little chart at the top of the page. It doesn't take long. And I'll guarantee after you've made this chart 3 or 4 times and used it, you won't need to make the chart, right? Or you'll realize it takes me 30 seconds to write the chart down and I don't have to worry about remembering it. And I know how to make the chart and now I have an easy reference, right? Either way, you'll learn it, okay? That's a big deal, okay? Okay, there are a few things that I do that are crazy that I think work. This is one of the things that I think is crazy, but I also know it works. And the reason I know it works is that when I give tests and quizzes in person, because now everybody just looks up online, whatever it is, but if you had to depend on remembering it, I'd say half of my students, I see this little blurb at the top of their test paper, meaning over at least half of my students realize it's important to write this at the top of their page because they know they remember it that way. All right, so now that we've taken the derivative, now I do apologize. Those of you, if you haven't seen my classroom, my board is actually quite a bit wider than what you see on the screen. Normally what I do at this stage is I write the derivative of trig functions over here. And those of you on the screen, you don't really even see me. But if you're here, you see I've got this whole big board I can write and just sort of leave it on the board for just reference for at least the first few days. All right, but now we need to apply this because, that's what we always do in math. We learn a little pattern and then we have to take the derivative. So that's what we're going to do. And so I want to start with y equals x minus tangent x. Everybody take the derivative of that. So the derivative isn't actually that hard. You just say y prime equals derivative of x is 1 minus derivative of tangent is equal to secant squared x. You go, what's the big deal? Well, the big deal is, wait a minute. We had to do some stuff with trig identities last year, right? Now, if you forgot the stuff with trig identities, that's okay, right? To be honest, the AP exam doesn't care about it anymore. 20 years ago, they did, right? 30 years ago, when I took the test, they did. They don't care about it now. So if you don't remember the trig identities, that's okay on the AP exam, right? If you forgot them, here's where they came from. So the primary one is this sine squared x plus cosine squared x is equal to 1. That's the big one, right? Like if you could not, if there's only one trig identity you ever remembered, this is it, right? That's the most important one. That's the only one I ever remembered from trig. It's called the Pythagorean identity because it's like a Pythagorean theorem. A squared plus b squared equals c squared. 1 squared is 1. And how you get the other Pythagorean identities, you look at this and you go, man, I don't like the way sine looks, right? I just don't like sine. And since I don't like sine, to get rid of it, I'm just going to divide everything by sine squared. So if I divide everything by sine squared x, sine, well, sine squared over sine squared is a 1. Cosine over sine is tangent. And 1 over sine squared is equal to cosecant squared. And I get another formula. And, well, if I don't like the way sine looks, I guess I could say, well, I don't like cosine either. since I don't like cosine either, I'll divide everything by cosine squared x. And sine over cosine gives you tangent. Cosine over cosine gives you a 1, and 1 over cosine gives you secant squared. Now that particular one's kind of handy because if you see 1 minus secant squared, you can manipulate this, so this ends up being negative tangent squared x. Now, one reason I'm doing this problem, not because it's on the AP exam, but because when I give you problems out of the textbook, here's how your textbook's created. I don't know why we have 10 editions, nothing's changed. Hardly, just so you know, your textbook is the 10th edition of this Larson and Hostetler calculus book. When I was in high school, I had the 3rd edition. And I still have that. So I look and it's like, okay, they added a few more things, but they get more money because they don't make new editions. So how calculus textbooks, they're usually written by a college professor. He writes the book, he writes the problems. And the answer key, he hands to a grad student. He said, all right, I need you to answer these thousands of questions. So the grad student answers all the questions. Now, sometimes these grad students like to show off what they know, particularly with trig functions, right? So when I assign problems that are trig functions and you do something and you get an answer that looks like this, but you check the back of the book and their answer looks like this, doesn't mean this answer is wrong. What it means is you've got a grad student who's showing off how many different rare trig identities they know to get this answer, right? I'm not going to mark this wrong, right? The AP exam accepts this, right? They accept this, the shorter answer too, right? So if you forgot a lot of those trig identities, particularly like the double and half angle formulas, that's okay, right? I'm just telling you because if you look in the back, if you look at the answer in the back of the book and you go, wait, that is not what I had. Well, yeah, it is. They just simplified it more. Sometimes I call it oversimplification, all right? So I would accept this. I'd accept this too, but you don't need to give me this. But this is the answer that would be in the back of the book. All right, now let's look at another one. Let's see, what if I give you y is equal to x times secant x? So everybody write that down and take the derivative. So I drew the line to just kind of refresh our memory on product rule. When you're dealing with polynomials, it's pretty obvious when you're doing product rule, because you've got little things in parentheses that are clearly multiplied together. What you're going to find as we see more and more different functions, product rule gets sneaky, right? Anytime you're multiplying two variables together, you're doing product rule. And by drawing that little line, you're sort of identifying, oh, I am doing product rule. I've got two things that are multiplied together. So once you've identified as product rule, then I can say, prove this guy is 1 times secant x plus this guy times root of this, which is going to give us secant x tangent x. All right? And honestly, I would accept this answer. If this was a problem, the back of the book would look at this and factor out a secant x. And so they would say this is 1 plus x tangent x. I don't know why they would do it, but that would probably be the answer they have in the back of the book. All right, so my sort of my goal, there's actually, I need to explain a little bit about your homework. Yes?
So when you're looking at terms, the derivative of secant x is secant x tangent x, and wouldn't you have a parentheses around the secant x tangent x because you're going to distribute the x into both of them?
Oh, no. That you can't distribute an x. A lot of people have trouble with that with the trig functions. This is not like secant x plus tangent x where you multiply an x times both. Everything is all one big thing. Like if I gave you a 6 times xy, would you say this is 6x, 6y? You could just call it 6xy.
Yeah.
Right? Because there's no plus. That's not, it's all like one big term. You don't get, there's no distributing this.
Okay.
This is the same thing as 6xy. Same thing over here. All right, so a little explanation about your homework. I assigned some problems, and the problems that I assigned, there are actually 4 major ideas. Right? One of the ideas is taking derivatives of trig functions, so those the first few questions are the other trig functions that you're practicing, tangent, secant, cotangent, okay. Then there's 3 other ideas. I'm not going to have enough time in class to teach the other 3 ideas. Right? What I am going to be able to teach is at least one of the ideas, and that's probably going to be it for the period. All right? So your homework, I've said it's due Monday, but basically it needs to be done by Tuesday because I've got to finish teaching stuff. The first part of it you can do, because it's like take the derivative of some trig functions. All right, so what do we do? So what's the next thing? Well, I want everyone to write down this function. So let's say I have y is equal to x cubed minus 5x squared plus 6x minus 4. All right, and I want to take the derivative. It's simple enough. You got a polynomial, we take the derivative. Well, the derivative of this thing is going to be 3x squared. Derivative of this thing is negative 10x, and the derivative of this is 6. Right. As long as you're adding or subtracting terms, you take the derivative of each term. Well, I want to take the second derivative. And so the first derivative, you get to put one little tick mark, and the second derivative, I put 2 tick marks, and what the second derivative is it's actually the derivative of the derivative. So if I want to take the second derivative, well, I take the derivative of this thing, which is going to give me 6x minus 10. All right? Well, while we're on this topic, if I want to take the third derivative, what do you think I'm going to do? What do you think the notation is going to be?
3 tick marks.
3 tick marks. And that's the derivative of this, and that's going to give me 6. Okay? And if I want to take the fourth derivative, guess what I do?
4 tick marks.
No, that gets ridiculous, right? Because after a while, you just can't give it tick marks, right? If you want the 10th derivative, does that mean you put 10 tick marks?
Did you write the Roman numeral?
No, you put a little 4 in parentheses.
That makes sense.
Well, because once you get past 3, can you imagine? Okay, the 6th derivative. That's just too much, right? So at some point, we have to give up on the tick marks and we use numbers, and the derivative of that gives you 0. All right, so now you get a little history lesson. All right, so a little history about calculus. So calculus is kind of a famous story where 2 mathematicians sort of discovered it about the same time, right? And of the 2 mathematicians, one of them I'll guarantee you've heard of, and the other one you probably haven't, right? So we're in mid, 1660-ish, right? And the one guy you've heard of is a guy named Isaac Newton, because everybody's heard of him, okay? The other guy is a guy named Gottfried Leibniz, and not many people have heard of him. Now, yes, you have? Oh, how have you heard of it?
I think Miss Dyche got a poster on our wall.
Oh. So here's why, now, Newton's done a whole lot of stuff, so I can't really trash talk Newton that much. But if you look at the documents where they sort of discovered calculus, if you look at the documents for Newton, you go, and you know calculus, when you look at it, you go, yeah, that's calculus, but it doesn't look like anything I learned in school, right? His notation is absolutely awful, okay? Leibniz, on the other hand, and I didn't do a great job of explaining this a while ago, but one of the methods you can say take a derivative is this thing where you put like a little script dy over a script dx. Okay? This is called Leibniz notation, right? And obviously we still use it because I've already referenced it. A little history behind Leibniz is, I honestly think the guy was probably crazy. He great mathematician, but his main focus was notation. What the man did is he said, I don't like the way we're writing it. So I'm going to change the way we write it. We're going to use different notation. And he said, all right, all of his mathematician friends, can you use this for a couple of months and tell me what you think? And then he would say, okay, they said, we like this, we don't like this. And he would keep changing things. So he'd keep revising. So much so that probably half of the whatever mathematical notation we currently use can be attributed to Leibniz. Because he just spent so much time on notation. The other guy that's responsible for a lot of the notation is a guy named Euler. He just wrote so much math stuff that whatever notation he used, they said, all right, that's what he used, that's what we're going to use. But as far as, I need to talk about Leibniz notation for just a minute. So another way that I could talk about derivatives is, I need to move this over. So one way to take the derivative is you could say dy dx. Okay? This is the first derivative. The second derivative is d2y over dx squared. You basically put 2's here and here. The reasons why you have to put a 2 here, a 2 in front of the d here, and a 2 in front of the dx on the bottom, I need to talk about parametric equations, and I don't talk about that in AB. That's talked about in BC. And then, obviously, for the third one, you'd say the d cubed y over dx cubed. And then the fourth one. Okay. So if you see this notation, like if you start seeing the dy and dx and you start seeing numbers, well, whatever number, that's the derivative you're talking about. Right? Just notation. So, okay, why would you take the derivative over? Because this gets boring. I mean, this is a very boring multiple derivative. They're called higher order derivatives. And this one's very boring. I mean, after the fourth derivative, you just get a bunch of zeros, right? Nothing interesting is going on. But what if we started with y equals sine x? And we took the derivative. So what's the derivative of sine x? Cosine x. And if we took the second derivative, what do we get?
Negative sine x.
Negative sine x. And we took the third derivative, what do we get?
Negative cosine.
Negative cosine x. The negative's decoration, derivative of sine is cosine, right? So I get negative cosine x. And if I take the fourth derivative, what do we get?
Sine x.
Because cosine's negative sine, we have the negative side. Well, that's interesting.
That's a cycle.
Yeah. It's like we start with sine x, and after we do 4 things, we end up with sine x, don't we? Well, that's weird.
It's like I.
That's actually my reference. You know, that's happened before. Right? If you think about I, and I squared, and I cubed, and I to the 4th, we call that I to the 0 is 1, right? And then I is just I, and then I squared is negative 1, and I cubed is negative I, and then you get to I to the 4th, you get back to 1, and it's just going that cycle over and over, right? That's interesting. I wonder if there's some sort of connection between these two. There shouldn't be, right? Because these have nothing to do with each other, right? I mean, because like this is square roots of negatives, and trig, that's dealing with the circle, right? They have nothing to do with each other. You're right, they don't have anything to do with each other. You know what else doesn't have anything to do with either of these? Is the number e. Right? Because remember e, that's like with logarithms, right? That natural log thing that y'all did a couple of years ago in a blink of an eye, that they don't spend nearly enough time. And actually, I don't need to look at the sine and cosine part. That's circles. No, what I'm going to do is I'm going to put 3 symbols. Actually, that guy Euler I talked about, he was the guy that kind of used these symbols, right? So the 3 symbols, like the 3 constants that you see in math a lot. You see pi, that's dealing with circles. You see I, that's dealing with like square roots and negatives. And you see e whenever you deal with logs, right? And those have absolutely nothing to do with each other, right? I mean, completely different things. If someone were to say you're going to learn these in the same chapter, you'd think, what the heck is that chapter, right? Because that's not what you did. This was in one chapter, this was in a completely different book, and this was in another chapter, right?
Chapter, weird cycles that kind of make sense.
Well, and I can't do it in this course, but in BC there's something called Taylor series. And when you do something called Taylor series, it's not like they're tailoring it. There's a guy named Taylor who came up with it. There's something you can do, but you need that level of math, so I don't teach it in this course. So even though these numbers have absolutely nothing to do with each other.
Teachers, at this time,
No.
please release the first half of
No,
the
I'm
class
not.
to report to seventh period.
You at home, you can't go anywhere. Sorry.
Mask up. Observe social distancing. and
So if you have e, it turns out e to the pi I is equal to negative 1.
Please wait
And if you
for-
type those in your graphing calculator, you do get negative 1. And this, to me, is the most amazing fact I've ever seen in math. Because they have no right to have anything to do with each other. They're completely different. And the beauty of math is the more math you learn, the more things you see get connected. And the first time I saw this was not in high school. It was in a upper level math course, and I still am amazed that, of course, you actually understand why it happened then. But it still amazes me that it's possible that these things have nothing to do with each other, can somehow be combined and end up with a pretty nice number. So what's your